All right, welcome back, guys. Today we're going to do one of my Excel challenges. When I was teaching, I quickly learned that many students had a great command of computer skills. They could do all sorts of things on their computer, but yet they really did not have a strong command of some of the productivity software like Excel and Word and PowerPoint. So I came up with some challenges that are chemistry related, of course, because it's chemistry class, that the students could do that would help them strengthen their Excel skills. So this is one of those challenges. I'm going to be introducing all of these in the next coming weeks. So tune in and let's get started. Okay, before we actually get to the challenge portion, we want to do a little bit of background so we understand where the challenge is coming from and how this challenge fits into what you've already learned about rate laws. First of all, let's look at a generic second order rate law. In this case, in a second order rate law, you'll see that the rate is equal to K, which is a rate constant, times some reactant times the concentration of another reactant. You guys are already familiar with this, hopefully, by this point. Now, one thing that we want to point out is that a rate constant is only constant for a given temperature. What? A constant is not constant? Yeah, that's correct. If you change the temperature of the reaction, then your rate constant actually changes. And so you can only use a rate law for a given temperature. Okay, so we know the rate constant is temperature dependent. And we also know that the rate constant has some sort of function of something that we refer to as activation energy. And you guys are already probably familiar with the basic concept of activation energy, but let me go back and let's take a look at a reaction and explain activation energy just so you have a good, clear understanding. Okay, let's look at a basic combustion of methane in the presence of oxygen. And we know as we move through this reaction, the first thing that has to happen before we can form products, we actually have to pull the reactants apart. We have to pull the individual atoms apart. And when we do that, that requires energy. We have to put energy into the system in order to get the atoms pulled apart. To break bonds requires energy. Now, when we remake those bonds into the products, then energy is released. Now, the energy that's required to break those bonds initially is what we refer to as activation energy. Okay, we're going to look at this in a slightly different way. Let's look at the regular reaction coordinate graph that you may have already seen, and let's see how this kind of fits in that scope. So let's do that same reaction. So when we break apart those individual atoms, you can see that it requires energy, and you can see we would refer to that as the activation energy. Of course, when we put those back as the products, energy is released. And as you know, or you may be aware of, if the energy released is more than the energy that's required to break the bonds, then the reaction is considered exothermic. If the energy released is less, then we would consider that reaction endothermic. Now, if we take a look at the Arrhenius equation, and I don't get bogged down too much in what looks to be a very complex equation, we can see that it breaks down the rate constant and it shows us how it relates to the activation energy, the temperature in Kelvin. We always have to be in Kelvin for this, and the gas constant. There's also what we refer to as an Arrhenius constant that is also sometimes called a pre-exponential constant in some literature, but here we're going to refer to it as the Arrhenius constant. Now, if we take this equation and we do a little algebra on it, and then we kind of split it apart, then this can be represented by your typical y equals mx plus b formula that you're very familiar with from algebra. And we know that m is your slope and b is your y-intercept. Now, we can get a little creative when we graph this, and we can actually use a standard graph to make a sloped line that we can extract. We can use a typical linear graph, and we can get a best fit line, take the slope and the y-intercept, and actually back calculate our activation energy and, of course, our Arrhenius constant. If you look at this equation, you can see in order to do that, we need to basically treat y as logarithm k. In other words, you'll have some values, and you'll have to take the logarithm of those values and use that as your y variable. And then you'll have temperatures, and you'll have to do 1 over the temperature to get your x values, and you'll graph those two to get your line. Okay, now let's look at the specific challenge. We're going to look at a reaction, the esterification of acetic acid with ethanol. Over on the right, you can see that you've got some actual experimental data at 4 different temperatures. The data was repeated 3 times at each temperature, and then an average was taken. So when you do graph this, you only have to use the averages. You don't have to do every single trial. Obviously, that would give you lots of extra data points. Just use your temperature versus your average K value. Also notice that your K is times 10 to the 4th. So you'll need to move your decimal place over by 4 in order to get the actual correct value. This was just done to make the numbers a little bit shorter for the table. Okay, so the challenge is you want to create a graph in Excel using logarithm K as your Y values and 1 over T as your X values. You want to add a linear regression to that graph, and you want to show the formula on the graph. And then you use your slope and your Y-intercept from your formula on the graph to solve for the activation energy and the Arrhenius constant. And in this case, we want to use the constant, the R value that gives us joules. So you're going to use the 8.314 joules over Kelvin mole for your R value. And that's going to give you the correct units for your activation energy, which would be joules per mole. So I think you guys can handle that. And if you have any trouble, there's lots of help out there to be able to create a graph in Excel and to be able to do a linear regression. Okay, hopefully that was enough information to get you started on this challenge. There's actually a download in the description below that you can download a PDF of this challenge so you can see the data and everything without having to continue to look at this video. And hopefully you'll be able to do this no problem. It'll give you some good practice with Excel, and I'll see you guys next time.